So if you just got started with dbt, you might be confused at the amount of materializations there are to choose from. So if you worked with databases in the past, you recognize table and view, but there are 3 others that might be pretty confusing to you. So in this video, I'm going to break down the 5 materializations in dbt and tell you how they work, what they do, and where they should be used. So if you're new here, my name is Mons, and I'm a dbt certified analytics engineer. And I work at a supply chain startup called Quiver, where I build the data transformations that power our product. And on this channel, I teach what I learned to help you accelerate your dbt learning. So let's jump into it. So the first materialization that we should talk about is the table. And this is the most common one. So a table, if you haven't worked with databases before, is just a collection of data, like an Excel sheet, that is stored in a database. So when you run a table materialization, this means that every time dbt is run, or every time the model is run, dbt drops the old table, it runs the SQL, and it creates a new one with the data that's selected from the SQL that you just wrote in the model. So this is a standard, and it's best used when you have complex transformations that are queried later in the data. So the pro of storing the data is that downstream transformations and models, and downstream just means models that reference this model as a source, if they have to do the calculations over and over again, as in a view, then it will get pretty slow. But if you're okay with having the data being as fresh as your last run, then it is a great option to do. So here in this code, I'm using table for my dimension customers. So this does a bunch of transformations or aggregations on each customer. So for this mock project, I created 2 seed files, which is basically just a source instead of having a database, because I'm just running this product. This project is run on DuckDB, which is just a very tiny version of a database that lives in a file, perfect for demos like this. And I have 2 source tables. So one with some customers. We have an ID, name, email, country, and created at as a date. And we have also raw orders, which is one ID for each order. We have the customer ID that made the order, when it was done, the amount, and the status could be completed, returned, or pending. So this is the data that we have to work with, that we got. So this customers table basically selects, makes a customer order summary with a customer, and it counts the total orders, it sums the amount spent, it gets the first order date, and it gets the most recent order date. So if this table was millions and millions of rows, it would be pretty complicated to calculate it each time it was queried. So let's say you have a BI tool that queries this model every single time. If it was a view, then it would have to do all of these calculations every single time. And in this case, it might not be as important to have the most up-to-date data, but you just store the information. So that's when tables make a lot of sense. Second one is views. So a view doesn't store any data. It is just a view in which you look at existing data. So a database would only store the SQL query definition. It wouldn't store the actual data. So every time this model is referenced or queried, the database reruns this SQL on the fly. So it doesn't store anything. This is just inline SQL that is run every single time. So when you want to use a view is when you have some kind of lightweight transformations where it's important that it gets the most recent data from the source. So let's say we run the DIM customers model. We run it once every day. But if we have some kind of table or some data where it's important that we see what's happening to the data all the time, like when we query it, we want to have it up to date, then a view would make more sense, because a view doesn't store anything. It just looks at the source directly. So here, in this case, for the customers, we only have a very light, just recasting, not even recasting, just renaming of the columns, just renaming ID to customer ID, name to customer name, and created at to created date. This is pretty basic, so it makes a lot of sense to just have this as a view. It doesn't need to be stored in a database at all. And the third one is the incremental materialization. And this is where it gets a little bit complicated. So the reason the incremental materialization was created was that if there was an orders table, let's say, or a table with a lot of rows, where a small amount of rows were being added every single day. So if you're a business that sells sandwiches, like in the Jaffle shop example, then if you have 10 million, 20 million rows, it costs a lot to just drop the entire table, like just remove all the information and then just assemble the table again every single time. We still need to store it. So then the incremental materialization comes in. And what it does is that incremental on the first run acts exactly the same as a table. It just takes the data from the source and it creates a new table and stores the result. But on subsequent runs, it looks at some kind of column where it tries to distinguish, or where you try to distinguish which rows are new and need to be inserted or updated, and which can we simply leave behind. So for this table, I've set the materialized to incremental, and I've set the unique key to order ID. And the unique key is basically only important for the model to know which rows it should update, but we'll get to that later. So we're using the staging model that we referenced earlier, we're gonna get to that, staging orders. And we basically just select the order ID, customer ID, select everything and have one reading, so very minimal. So the first time this is done, it just selects everything from orders, which is staging orders, pretty normal. But let's say this staging orders has 10 million rows. And first time we create it, we get all of those 10 million rows into our target table. And the second time, there are 10 million, 100,000 rows. And we don't want to just drop those rows as we normally would with a table. What incremental does is that it allows us to put a filter, or a filter on the source. So this is the important clause to look after. If is incremental. So this is a Boolean that is true on every subsequent run that isn't the first. So this is false on the first run, then it would get all of the source data. But on the second one, this would evaluate to true, and then we would insert this code. Where order state is larger than select max order date from this. So there are a few things happening here. This is a keyword that references the table of the model. So what this is comparing is basically, in the source, we have 10 million and 100,000 rows. And in the target table, this is the pointing, the table, it would select the max order date from this. So the max order date, maybe that was yesterday, if we ran the model yesterday. That would be yesterday, the 11th of April, and it would only select orders where the order date is larger than that. So it would automatically use the indexing of the database of the table to select only the newest orders. This way, it doesn't have to go through all the 10 million ones. And you can find unique ways to do this, but this is a pretty simple way to do it. You can have order date, created at, updated at. Those are usually pretty good columns to use. But yeah, incremental table, first run, and second run, you choose what data gets inserted into it. And unique key, that just determines which row you should update. And now we get to the almost last materialization, which is ephemeral. So an ephemeral model is something that never reaches the database. And what this means is that if we have an ephemeral model and a table model that references this model, then this will never get materialized in the database, but it will get inlined as a CTE inside of the model. So it's basically just a way to write common functions or common expressions that might get reused across several models, but you don't want to really show up in the database. Like, it doesn't really help anyone. It's only helpful inside some other model. Like if you're a programmer, like a function would be used somewhere else, but you don't really need to see the function, you just need to use it. So yeah, ephemeral models are never written to the database. So it inlines SQL as a common tables expression. And the best case where you should use them is for some kind of intermediate logic where you have some kind of transformation that you want to do, but it isn't really helpful to expose. So So yeah, notice here, after you run dbt, you won't find this model in the database. So for this one, in the example project, we have staging orders. So this model just does a very light cleanup. It has one recasting and one where clause where it sorts out orders where the status is returned. So this isn't, in the example, isn't really helpful to expose or to look at in some other place. But when we have the facts, this is referenced. So this, according, if we look at this, it would basically just copy whatever we had in here instead, and then it would run dbt normally. So that's basically what ephemeral models do. And let's move on into the last materialization. So that is the custom materialization. So dbt core only supports four materializations, but it still allows you to make your own materializations. And this means that you write the SQL code that will be run on the database. You can customize everything, literally everything. This is trickier to use, but if you have some kind of special use case, then you can definitely make it with custom materializations. So for this example, I have a revenue summary, and this model that uses a custom materialization, good thing to know is that they're put in macros, and then you just declare them with this statement, materialization, the name and default, and then you end them with end materialization. And then you define all of the DDL that is then run on the database. So this looks pretty complicated, but let's walk through it. So the reason that this one was created is to have a kind of backup to a table. So if you have a model where it's important that you have a backup of whatever you do, like maybe you screw up some source data and you run, and you're in situations where you want to be able to go back to the last table that you generated, then you can create it with a custom materialization. So what this one does, the table with backup, is that before it drops the table to create a new one, it changes the name to whatever the name was plus backup, and then it drops the table no, it doesn't drop it. Then it creates the new one. So we would get both a revenue summary and a revenue summary with backup. So that is what existed before the run. And this can be reused. If you create it once, you can just reference it. You see here, we set the config to table with backup. And in this case, we import customers, we import orders, and the summary is basically the customer ID, the country, and then the different things are connected to the country where the customers are from. So if you run this twice, then you might get different results if the source data was changed. And that's just one example to what the custom materialization can do. At Quiver, we use this to maintain referential integrity, which basically means that we have rows that reference each other. And if we drop the table, then those references break, and we want to make sure that they don't. So we have a unique insert pattern, and that's how we use the custom materialization. And those are the 5 different materializations in dbt. I hope you enjoyed the video, and I'll see you in the next one. Bye.